So let's go ahead and look at the first one together. So the first one says, rainwater pours off a roof. Rainwater pours off a roof into a cylindrical barrel. When it stops raining, water leaks out of the barrel at a rate proportional to the square root of the depth of the water at that time. And there's a part A and a B here. Part A, write and solve a differential equation for the depth of the water, W, at time t measured in hours. Let's do that part first. So, Co-16C, there is a palindrome for 24, 24. So when I read this question, I'm just going to try and like set up the, I don't need to write it all down. I'm just going to try and figure out what's going on. So I see I've got rainwater pouring into this thing. I've got a cylindrical container. It might be important. It's a cylinder. It might not be. And it's going to rate, the water level is going to be, it's going to rain. Water is going to pour in. You're going to get to some water level up here. It's stop raining. Then it's going to start leaking out. And they say that it's going out, so the water is leaving. I am going to write this right down. Water is leaving at a rate proportional to the depth of the water at time t. Okay, which we're calling W. Because they told us to. Really, you can pick any letters you want, but if they tell you to use a certain letter, you can do that. So I'm thinking of, okay, the depth of the water is W at time t. And I wrote kind of the wrong words, I think, right? I think I forgot an important word. They say that the water leaks out of the barrel at a rate proportional to the square root of the depth of the water. So that's real important. So at first glance to me, it looks like we're going to say, okay, the rate of change of the depth of the water, so the rate of change of W, is going to be proportional to, just means multiple of. So I like to use K typically. You can use whatever constant letter you like. The square root of the depth. And at least in this first part, we're not given any other information. So that's our setup. And then we're supposed to solve for the depth of the water. All right, so this looks separable to me. I'm going to bring all the W's to the left, all the T's to the right. Here's part A. We're going to separate. So we're going to have dW divided by the square root of W equal to K times dt. And before I start trying to integrate this, I would definitely rewrite it as W to the negative 1/2. So let's rewrite this as W to the negative 1/2 dW equal to K dt, and then we'll integrate both sides of that. So then we're going to anti-differentiate. The antiderivative of W to the negative 1/2 is going to be W to the positive 1/2 divided by 1/2 is multiplied by 2 equal to the antiderivative of the constant K is K times your variable T plus another constant C. Reading this first part again, the first part says write and solve a differential equation for the depth of the water. So here's our differential equation to start. And we're working towards our solution. We still have to solve for W. So I'm going to divide both sides by 2. Now, here's where you can kind of go one of two ways. If I divide everything by 2, the right side of my equation is going to look the same. A constant divided by 2 is still a constant. Constant divided by 2 is still a constant. But you want to feel like you're maybe tracking your work better. I would encourage you to say that this is K1 and this is C1. And then when I divide both sides by 2, W to the 1/2 equals K1 divided by 2 is a new constant. Let's call it K2. And C1 divided by 2 is a new constant. Let's call it C2. You really don't have to do that, but some people really kind of feel better when you do it that way. Or you just call them all K and C the whole time. Or you could write K1, K over 2 and C over 2 if that's better. Really like anything you pick. And then finally, we're going to square both sides and say that W is equal to this whole quantity, K2 times T plus C2 squared. And if I'm writing my final answer, I might write this as W of T is equal to the constant times T plus another constant 1V squared. And as far as part A is concerned, that's all we can do. They didn't give us any initial conditions that allow us to figure out what our constants are.
Can you explain why like the two is negative?
Sure, yeah. So wait, why the two? So like right here when I answer differentiated. So whenever you do this, you add 1 to the power and then you divide by the power. So really what I've got here is W to the 1/2 divided by 1/2.
Okay.
And that's just multiplying by 2. So really dividing or multiplying by a positive number doesn't change the positivity here. Yeah, interesting. Okay, sure. Sorry, I was having a thought that was not correct. So then the part B of this says, if the water level drops from 36 inches to 25 inches in 4 hours, how long until the barrel is empty? So I'm going to imagine that at time equals 0, that's when we have 36 inches of depth. So I would make a little table like this. Time and depth. The time equals 0, the depth is 36 inches. 4 hours later, the depth is 25 inches. So I can plug those data points in and figure out my constants K2 and C2 are. So I plug in 0 for T and 36 for W of T. I'm going to have that 36 is equal to K times 0 plus C squared. So it looks like, that's interesting. It looks like 36 is equal to C2 squared. So it looks like C2 could be positive or negative 6. That seems kind of strange to me. But I'm going to probably assume it's going to be positive if I don't have a good reason not to. So I would say that my constant here is probably going to be 6. But I might kind of start thinking about just keeping that, well, maybe it's negative. Let's figure out. So then if I plug in the other one, W is going to be 25 when times equal to 4. So I'm going to 4 times K2 plus 6 squared. So square rooting both sides, I have 5 equal to 4 times K2 plus 6. So it looks like K2 is going to have to be -1 divided by 4. Interesting. Yeah, that is interesting. I feel like there's something to say here that I'm missing. But I would, if it were me, I would assume when I was square rooting these things, I was getting a positive value because, well, that's the safe assumption. But again, feels like it could be a little dicey here. Let's plug this in and see what we've got. So rewriting our solution with now K2 equal to -1/4 and C2 equal to 6, we've got the depth at time T is going to equal -1/4 T plus 6 squared. That seems all right. The values work. W of 0 is certainly 6 squared, which is 36. And W of 4 is certainly -1/4 times 4 plus 6, which is -1 plus 6 squared, which is 25. And it seems like as time goes on and on and on, the water depth will get lower and lower and lower. So then the question that they ask is, how long until the barrel is empty? Meaning, how long until W equals what? Right, we want the depth to be 0. So we're going to set W of T equal to -1/4 T plus 6 squared equal to 0. And we're going to end up finding that -1/4 T plus 6 has to equal 0. So 6 equals 1/4 T. So 24 equals T. So 24 hours or 1 whole day. Interesting. So it certainly seems like this, what we did was correct in that our answer seems like a reasonable answer, right? We didn't get a negative value for time. I feel good about that. So like we did the right thing. questions about this one before we do another one? If I were an instructor, I would probably ask a tank problem because they're pretty typical. I would not call this a tank problem. Tank problem meaning you got stuff going in, you got stuff coming out at certain concentrations, which the next problem certainly is an example. So, and I guess for people watching the video later, if people are watching the video later, I'll post these word problems as well, so you can like refer to them when you look at it, so you don't have to be like, what's he talking about? Why is he writing things down? So we've got all these word problems right here. So here's the second one. And let's write down the pertinent things. In fact, I want you to, well, we'll all write down the pertinent things as we go along. So a tank initially contains 100 gallons of water containing 1/4 pound of salt per gallon. So in the beginning, my tank, which I don't really know the shape of it, but it doesn't really matter, contains 100 gallons of water and 1/4 pound of salt per gallon, meaning I have how much salt? Well, 1/4 pound of salt per gallon times 100 gallons is going to be 1/4 of 100, which is 25 pounds of salt. I would always, with tank problems like this, or with kind of differential equations in general, we always are kind of thinking about the differential equation in terms of how much salt there is, not the concentration of salt. So they told us that there was 1/4 pound of salt per gallon, and then we had to definitely translate into the, that means we have 25 pounds of salt in the tank. And then we're putting in a saline solution with a concentration of 3 pounds per gallon at a rate of 5 gallons per minute. So going into the tank, we have a solution that's going in at 5 gallons per minute with a concentration of 3 pounds per gallon. That sounds like a lot of salt in your gallon of water, but okay. And then we are draining it. Oh, I'm going to change this one. Yeah, sure. No, I won't change it, I guess. So we're draining it at 7 gallons per minute with a concentration, and so the draining part is the concentration, is always what the concentration is like the challenging part. To me, it's the most challenging part of the setup. So the concentration is just, I would write it this way: the amount of salt in the tank divided by the volume of the tank. That is always going to be the case. In any problem like this where you have to solve it, the volume of the tank should be constant. This one we're not going to solve, we're just going to set up because, well, that's what the question asks. So I should finish reading the question. It says set up in bold, or not bold, but capital letters, a differential equation with initial condition, which describes the rate of change of Q of T, the number of pounds of salt in the tank anytime T.
So we're not gonna get a question like this on the test?
Not exactly like this. Well, so I would say you can get a question like this that asks you just to set it up. And the reason this is just a setup as opposed to a solve is because you've got 5 gallons going in per minute and you've got 7 gallons going out. When the volume is changing, it becomes extra difficult to solve.
There was a question like this.
There was, but it only asks you to set it up, I'm pretty sure. I'm fairly certain that we can go back and look later, but I feel like someone asked me to take a look at that one specifically, and I did, and I was pretty sure it said to only set it up. So anyway, we can talk about how you would solve it, but I feel like it's not actually too terrible. So in this case, we're saying, they told us to say that Q of T is the amount of salt in the tank at time T. So the amount that's going out is going to be 7 gallons per minute times the concentration of salt in the tank, which is going to be Q of T pounds of salt at whatever time T, divided by, well, the volume is changing. Every minute that this process goes on, we're going to lose 2 gallons in our tank because we're putting in 5 gallons every minute and we're taking out 7 gallons every minute. So the volume of the tank is actually 100 gallons minus 2 times the number of minutes that have passed. So our setup here is going to be that, sorry, our setup is going to be that dQ dt, the rate of change of the amount of salt, is going to equal the rate in minus the rate out. And that's just going to be what we just found. The rate in is 5 times 3. I like the units here. It helps me make sure I've got things right. I can see that, oh yeah, I'm putting in 15 pounds of salt every minute. Seems like a lot of salt. Minus the rate out, and then my parentheses there. The rate out is going to be 7 gallons per minute times Q of T pounds per 100 minus 2T gallons. Or writing it without the numbers, dq dt is equal to 5, or sorry, not writing it without the units, not without the numbers. We need the numbers. Is 5 times 3 minus 7 times q over 100 minus 2t. Yeah. And this one is challenging. Yeah, it's a bit challenging. So you could solve this one. It is not impossible. It's actually not, it's not like super terrible. So I will point out, if you wanted to solve something like this, you would have to use a first order linear differential equation. So you would have to write this as so I don't think we have to solve one as challenging as this, but if we had to solve it, here's how we would do it. If we have to solve, we're going to rewrite this as dq dt plus 7 over 100 minus 2t times q equal to 15. So that we have our usual first order linear differential equation setup. You have your q prime plus your function of t times q equal to 15. And then we could do the usual thing, right? This left-hand side, this is supposed to be, oh, sorry, I always jump the gun here. We would then multiply both sides by the integrating factor. So say, okay, great. We're gonna have I times q prime plus I times 7 over 100 minus 2t times q equal to 15 times I. And then this left-hand side here is supposed to be I times q prime plus I prime times q. Meaning I prime has to equal I times 7 over 100 minus 2t. And then we can separate variables. This is really di dt equal to all that. Bring the I down to the left. So you got 1 over I di equal to 7. So I'm going to do something. I'm going to do a small thing here. Instead of writing 7 over 100 minus 2t, I'm going to write 7 over 2 times 1 over 50 minus t, just to make it slightly easier to find the antiderivative. I'm just factoring out the 2 from the bottom. And then we're going to anti-differentiate both sides. On the left-hand side, we get the natural log of I. On the right-hand side, we get 7/2 times the natural log of 50 minus t divided by -1 times -1. Reminder, when you're finding the integrating factor, you don't have to worry about any absolute values or any plus c's or any of that jazz. You're just trying to get I very simply. So then, yeah, so this is where things are going to get terrible. If we rewrite this as the natural log of 50 minus t to the -7/2 power, then our integrating factor is not very nice. It's e to the, sorry, it's not e to, well, it is e to the natural log of 50 minus t to the -7/2, which is just 50 minus t to the -7/2. Which I guess is not the worst thing ever. All right, we're actually almost there. We might as well finish it. So then we're going to say that this left-hand side here really is the derivative of I times q, and it's equal to 15 times the I that we just found. So then I times q is equal to the integral of that. Let's put the 15 on the outside. And then I should probably write what I actually is, because I had, but we're gonna get Q equal to 15 divided by I times the integral of this, which also isn't that terrible. It's just the reverse power rule. It's 50 minus T to the -7/2 plus 1 is -5/2. Divided by -5/2 is like multiplying by -2/5, but then it's also going to divide by a -1 because of the negative T there. So it's going to be times a +2/5 plus C. Gross. And then finally you'd plug in what I was, and since I don't have enough room down, I'm going to write it up here. And we're going to get Q of T equal to 15 over this 50 minus T to the -7/2. You shouldn't write it that way. You should write it as 15 times 50 minus T to the +7/2. And then times all that. Okay, it's more than I really wanted to do there, but it's fine. And then I'll point out that if we wanted to figure out what C was, we use our initial condition, which is that at time 0, there were how many pounds of salt in the tank? Right. So you'd plug in 0 for T, 25 for Q, and then you'd solve for C, which is probably awful. That's probably not that awful, actually. And be careful there. I wrote 5 over T, that's 5 over 2. Sorry about that. Okay, so that one's a little extreme. I guess not unreasonable. If it were me, if I were asking this question on a test, it would be an extra credit question because I feel like it's more than challenging. Okay. Let's look at this next one. This next one, so the hard part about a lot of these word problems is there's a lot of words, right? You have to read the words kind of carefully. So let's look at this next one, which has a lot of words. So here we go. Number 3. A demographer is trying to model the population of a particular region. To do so, she wants to consider both births and deaths as well as net immigration into the population. The population is spelled wrong. Oh well. Suppose that due to births, the population increases at a rate proportional to the size of the population with a constant of proportionality B. So I'm going to write that down. So population is increasing at a rate proportional to the birth rate. Right, that's what that said. Yeah, the due to birth, the population increases at proportional to the size. Oh, sorry, let me say that again. Population is increasing at a rate proportional to the population size. And the constant of proportionality is B, with B as our constant. So what that tells me is that I'm going to have something like dP dt, the rate of change of the population, equal to B times P, proportional to the population size, and B is the constant of proportionality. That's not all though. That's not the final equation. So then we're also told that suppose further that the population decreases due to death at a rate proportional to the size of the population with a constant of proportionality D. So population is decreasing at a rate proportional to the population with D as the constant. Now, I know what the answer is supposed to be here, but the person writing the question who wasn't me. The person writing this question should have specified that D was positive, because otherwise you could just be like, well, I'm going to think of D being negative, and then you could say that dP dt is just equal to D times P. That's not really correct, because we want to essentially, we're subtracting off that amount. So we really want to think of it as being minus that. And again, really what we're going to do is we're going to combine these all together in one equation. So these are just kind of what we're thinking. We're thinking this, and then finally, lastly, suppose that there is a constant number of people per unit time moving into the region written as N. So population is increasing by n per unit of time. So we're going to be adding n. So it seems like our differential equation, taking all of this into account, should be the rate of change of the population equal to b times p minus d times p plus n. It's increasing at a rate that proportional to the population, the rate of constant proportionality is b, decreasing at a rate proportional to the population, and the constant proportionality is d, and increasing by n every unit of time, again, which has not been specified. But this is kind of the idea, is we're just trying to take this information and write down a very generic differential equation. Personally, I think if you wanted to, you could say that dp dt is equal to b times p plus d times p plus n if we specify that b is positive and d is negative. Or you could just say in this one here, both b and d are positive. Kind of a weird question. Let's look at another tank, because I feel like another tank problem. I would ask a tank question. Maybe I'm biased. I like the tank questions. I think they make you think. So let's skip number 4 for a second and go on to number 5. So here's what we got. A large tank contains 700 liters of a salt solution, which has a concentration of 0.65 kilograms per liter. So we've got our tank. It's got 700 liters and it's got 0.65 kilograms per liter, but I want to be talking about how much I have, not my concentration. So 0.65 times 700. Ugh. Good question. Well, I know times 100 would be 65. So 7 times 65. 7 times 60 is 420. 7 times 5 is 35. So it's 455 pounds of salt. That's our initial condition, by the way. So we know that S of 0, because we're going to use S here instead of Q. We know that S of 0 is 455. And sorry, I wrote pounds, but it should be kilograms. Apologies. Right, we're given that it was 0.65 kilograms per liter, not pound per liter. You might notice that when I read these problems, I like to write this stuff down as I go. Right, I read a piece of information. I thought that was important, so I wrote it down. So then after that, we're being told a salt solution which has a concentration of 0.8 kilograms per liter. So we're putting in salt with a concentration of 0.8 kilograms per liter at a rate of, is added to the solution at a rate of 60 liters per minute. We are taking solution out. At the same time, the solution drains from the tank at also a different, I'm going to change that to 60 liters per minute because I want one that's more typical. We're draining it also at 60 liters per minute. And the concentration that we're draining it at is going to be the amount of salt in the tank at time t divided by the volume of the tank, which is 700 liters, and it's not changing because we're putting in 60 liters per minute and we're draining out 60 liters per minute. And yes, it did change the amount going out to be 60 liters per minute. So let's set up the differential equation. In fact, I want you all to set up the differential equation. So set up the differential equation, you're going to have ds dt equal to the rate that salt is going in minus the rate that salt is going out. Give you a minute or so to do that. here's how things are looking to me. The rate the salt's going in is gonna be 0.8 times 60 kilograms per minute. The rate the salt's going out is gonna be S of T times 60 over 700 kilograms per minute. So we want to simplify this so it looks like something we can actually deal with. I like to write it, you don't need to write it with the units, but I like to write it with the units just so I can see, oh yeah, I'm getting kilograms per minute because the liters are canceling, I'm getting kilograms per minute because the liters are canceling. They should be the same rate of type of rate with units. So my DSDT here is going to be 0.8 times 60 is going to be 48 kilograms per minute, which I'm not going to write. Minus, here I would simplify this a tiny bit. I'd write this as 6 over 70 or even 3 over 35. I like to reduce, yeah, I like to reduce my fractions. It's gonna be 3 over 35 times S of T. And in this situation, you do have a choice. You could solve this either by separating or by doing first order linear. Let me show you what I mean. I know last time I said this, I said, let me show you both ways, and I didn't show you both ways. Let me show you both ways actually this time. So we could do it as first order linear by writing it as ds dt plus 3 over 35 times S of T equal to 48, or more typically S prime plus 3/35 S equal to 48. So that's the usual kind of setup for a first order linear. Or if you want to do it as a separation of variables, I feel like separation of variables actually might be harder here. Because if you want to separate this, you have to write the right-hand side, essentially factoring out the S. So I need to write this as a fraction. Well, factoring out the S is maybe not the right way to say this. Yeah, it's ugly. You could do it this way and say that ds dt equals 48 minus 3/35 times S. And then here's what you're gonna get. You're gonna get ds divided by all of that equal to dt. And yeah, you can make it a little less terrible by multiplying, or essentially by factoring out a 1 over 35 here and saying, but like it just feels like really terrible. Like, I don't really want to say that ds over 1 over 35. Let's see, what's 35 times 48? Good question, right? 35 times 2 is 70. 70 times 24 is, right? It just feels like not good. So I would actually probably recommend, not that it's impossible to do it this way, but I think it's easier to do it this way. Especially when the thing that's multiplying by S is just a constant. This feels very straightforward to me. So here, and then I feel like I should do this though. 48 times 35. 5 times 8 is 0, 4, 5, 24, 0, 3, 4, 2, 12, 14. So you could write this as kind of weirdly 1 over 35 times 1,680 minus 3s. And then you could integrate both sides of that. So on the left-hand side, you've got 35 ds over 1,680 minus 3s equal to dt, and then you can integrate both sides. It feels messy. So I would generally recommend for a tank problem, whether it's one that can be solved by separating or not, to not, right? Solve it with the first order linear method. So here, doing it kind of the nicer way. And I don't actually know, has Dr. Berg specified that she wants you to show all the work of finding I on an exam? Like you're expected to find I by first multiplying both sides by I, like this?
She hasn't really said.
Okay.
Just that she needs us to know how to do it.
Okay.
I saw someone ask.
Sure. It makes you think she might ask a question that kind of specifically gets you to have to do that.
Because someone's asking her, she's like, You can, but I prefer to.
Right.
And when we do it faster. then
Right.
we have to-
So it sounds to me like you should know how to do it this way, is what that says to me, right? So I would certainly recommend doing this and then observing that this needs to be I times S prime plus I prime times S, which in this case means if you have like a different colored pen or something, like, oh yeah, this here and this here have to be the things that equal each other. So that this whole thing works. So then we're gonna say, great, I prime or di dt has to equal 3/35 times I. I will point out, because we've seen it enough times, that when you have the derivative of something equal to just a multiple of the original function, the solution is always this e to the kt thing, where k is that constant proportionality. So we can see here that I of t is going to be e to the 3/35 t. You can show the work, right? It's certainly fine to say, oh yeah, the integral of 1/I di is equal to 3/35, the integral of 3/35 dt, and then get the natural log of I equal to 3/35 t, and then e both sides to get I equal to e to the 3/35 t. But I feel like that one is so common that you could probably not show all that work if you really didn't have the time to. And then we keep going, we get that our I times S prime is equal to 48I, which means that I times S is equal to the integral of 48I dt. And then we should plug in what things are. So our integrating factor is e to the 3/35 t. So we have e to the 3/35 t times S equal to the integral of 48 times e to the 3/35 t. And then it's just a couple more steps. We integrate, we have S equal to 1/e to the 3/35 t. And the integral of this is just going to be 48 times e to the 3/35 t divided by 3/35 or multiplied by 35/3. Kind of terrible. Plus c. And again, if I'm taking an exam and just trying to find a solution, I'm stopping there. I don't have a great desire to figure out what 48 times 35/3 is. If we were asked to figure out what C was, we would need to go back and plug in our initial condition and be like, oh yeah, S of 0 was 455. So then we could plug in T equal to 0, S equal to 455, and get that 455 is equal to 1/e to the 0 times 48 times e to the 0 times 35/3 plus c. So it looks like 455 minus 48 times 35/3 is equal to our constant c. Again, I wouldn't try to find that if I didn't have to. I know Dr. Burke is a pretty rational person. I think she would, if she, first of all, I don't think she would give you quite such terrible numbers, but if she did, she wouldn't expect you to then be like, yeah, I can totally do that without a calculator. So I would leave it like that. Questions about this, by any of this? I noticed that we talk about word problems and graphing today. There's not a lot of time left to talk about graphing, but let's talk. There's one thing I will say about graphing in the last 6 minutes we have here. So, yeah. Out of order. So I make sure things too out of order here. Okay. So let's look at one example here that I had teed up. Just the following. So let's say we're given the following surface. X squared plus y squared minus z squared equal to -9. And we want to find the traces. So traces in each of the coordinate planes. So the thing I really want to say about this is finding the traces. The first step is always straightforward. If you want to find the trace in the XY plane, what's the first thing we do? We set Z equal to 0. That's the first thing we do. Always the odd variable out is when we set equal to 0. And in this case, it's actually kind of disappointing because when we do that, we get x squared plus y squared equal to -9, which doesn't have any solutions. So no solutions means no trace. Sometimes we then go ahead and ask about what about like planes parallel to the xy plane, which means you're just setting z equal to a different constant. So if you set z equal to something like parallel to the xy plane. So if we set z equal to something like, I'm gonna pick a number bigger than 3, so I get something that works out. So if I set z equal to something like 5, then I'm gonna get x squared plus y squared minus 25 equal to -9. And adding 25 to both sides, I get x squared plus y squared equal to 16, which is the equation of a circle of radius 4. So my level curves are circles. My level curve is parallel to the xy plane. Although when someone says level curve, if they're not specific, they usually mean parallel to the xy plane because that's kind of viewed as the up-down direction. Although you can certainly have level curves parallel to the xz plane and to the yz plane as well. So let's look at the other two traces. So let's look at the yz plane. Mostly just because it's the one that's easier to draw if we're going to actually try to draw the three-dimensional shape. So in the yz plane, we're setting x equal to 0. And we're getting y squared minus z squared equal to -9. Which is going to be a hyperbola. I personally would choose to rewrite it as z squared minus y squared equal to +9. Just because it feels better. You don't need to do that, but it's easier for me to see that, oh yeah, that means that the hyperbola is going to intersect the z-axis, not the y-axis. So I try to draw, I didn't draw this because there was no solution. So if I draw this here, I'm getting a hyperbola where the z-intercepts are plus or minus 3. And then we're hyperbolaing away from the center. And in this case, we don't really need to talk so much about planes parallel to the YZ plane, because if we change the value of x, we're just going to get a different hyperbola with that's further away from the further away from the center. Let's check. If I plug in x equal to 2, I'm going to get 4 plus y squared minus z squared equal to -9. Look at y squared minus z squared equal to -13. Or z squared minus y squared equal to +13. So yeah, this one would be a hyperbola further away from the center, which makes sense. Usually the one at the coordinate axis plane is the one that's like the closest in. And then very, very similarly in the xz plane, we're going to get virtually the same thing. We set y equal to 0, we're going to get x squared minus z squared equal to -9. Or z squared minus x squared equal to 9. Another hyperbola. The thing I want to say about this is, if you memorize kind of how the quadric surface equations look, you might get tricked by this. Because when I memorize them, I'm like, oh yeah, I know that everything's squared. If everything's squared and positive, it's an what's the word here? Not an ellipse, but an elliptical. What is the word? An ellipsoid. Sorry, an ellipsoid. And if they all have the same coefficient, then it's a sphere. But if one of them is negative, usually that means you have a hyperboloid of 2 sheets. but we're getting, oh, sorry, hyperbola of one sheet, apologies. But that's if it's positive over there. So it's a hyperbola of one sheet. If it's x squared plus y squared minus z squared equal to a positive number. But since it's negative here, we really would have to multiply everything by -1 and then have a negative x squared minus y squared plus z squared equal to +9. And that would be a hyperboloid of two sheets because you have two negatives, not one negative really. So this question often is kind of tricky if you memorize the quadratic surface equations. But again, really, you shouldn't just be like, I memorized it, this is the answer. You should be like, let me show the work, let me find the traces. So here, what this would end up looking like is, we got a minute here. So can I draw this? Maybe. Yeah, I can draw this. So we're going 1, 2, 3 up, 1, 2, 3 down. I might just draw the top part. So in the YZ plane, we have this hyperbola. Draw some different color here. And down there, same deal. And then in the XZ plane, we also have the same hyperbola, which I know I didn't graph because it was the same equation. So in the XZ plane, you've got hyperbolas kind of coming out at you. So which is never the easiest thing to draw. Going back like that, and coming out at you like that. Same deal down here. And then in planes parallel to the XY plane, you have circles. So we go up a little bit, you've got kind of a circle. Yeah. Woof. Yeah. Okay, that's kind of there. So that's the idea. You have a hyperboloid of two sheets, or as I like to think of like two satellite dishes kind of facing away from each other.